Hi guys, this is section 6.3 where we talk about how Helmholtz energy and Gibbs energy depend upon pressure, volume, and temperature. Um, so we defined Helmholtz energy A, constant temperature and volume, and Gibbs energy G, constant temperature and pressure. But that doesn't mean that the temperature has to stay constant for the whole process, and likewise for the volume or the pressure. It just means that the initial and final temperatures have to be the same, and for Helmholtz energy, initial final volumes, Gibbs energy, initial and final pressures. So what we're going to do here is, see how Helmholtz energy and Gibbs energy depend upon these variables: temperature, volume, temperature, and pressure. These are real useful to chemists because they let us know which direction a chemical reaction is going to proceed spontaneously. So we showed already in the last section these equalities here. Partial A, partial T, constant V equals negative S. Partial A, partial V at constant T is equal to negative P. So, starting there, we can see that what we know is that entropy is always positive. You can't have negative entropy. Likewise for pressure, the lowest pressure you can have is zero, an absolute vacuum. You can't have negative pressure. So because entropy and pressure are both always positive, and from these equalities we see that if temperature increases in constant volume, that means for this equality to hold true, the Helmholtz energy must be decreasing. Likewise, if temperature decreases at constant volume, Helmholtz energy must increase, okay, for this equality we did true. Likewise, with respect to volume, okay, if volume is increasing, that means that the Helmholtz energy must decrease. If the volume is decreasing, the Helmholtz energy must increase. Partial A must be positive. Looking at other equalities that we derived in the last section, partial G, partial T, constant P equals negative S, partial G, partial P, constant T equals V. Doing the same sort of analysis because we know that entropy is always positive. Likewise, you can't have a negative volume. If temperature is increasing, that means delta T is partial T is positive. That means that G, Gibbs energy, must be decreasing. Partial G must be negative. Likewise, if temperature is decreasing, partial T is negative, then Gibbs energy must be increasing. Partial G must be positive. Over here, because there's no negative sign like there was before, we see that if pressure is decreasing, Gibbs energy must decrease. If pressure is increasing, Gibbs energy must increase. So useful things to remember. So now let's look at how Gibbs energy changes when we change the pressure at constant temperature. So starting with this equality, again we derived this last section, partial G, partial P, constant T equals V. Multiply through by partial P, making these exact differentials. You see that dG equals VdP, and integrate over pressure from initial pressure to final pressure. We get this. This is just saying that whatever the Gibbs energy is at, again, temperature is constant at that temperature and the final pressure, minus what the Gibbs energy is at the temperature and the initial pressure. That's what the integral of dG is, delta G. It's equal to integral of VdP from initial to final pressures. Now, if we're talking about a solid or liquid, we can say that the volume doesn't really depend on pressure, it doesn't really change. So it's a constant, we can pull it out and we just get the integral of VdP is equal to V times the final minus the initial pressures. It gives us that the difference in the Gibbs energy at the final pressure minus Gibbs at energy at the initial pressure, temperature being constant, is equal to V times delta P. Or rearranging this a little bit, we can see that, and this is where it's starting to get useful. The Gibbs energy at some pressure, should have an F right here, final pressure right there, is equal to the Gibbs energy at the initial pressure. Usually this one here is whatever we look up in the tables, 1 bar. plus V times the final minus the initial pressures. So if we set the initial pressure equal to 1 bar, then we have standard states, and so we can say G at whatever temperature, 298.15 actually, and the new pressure is equal to standard Gibbs energy, 298.15 Kelvin, 1 bar, plus V times the final pressure minus 1 bar. That's for solids and liquids, remember? So this is a useful equation in blue or purple or whatever color that is right there. Now, for gases, okay, we know that the volume does depend, dramatically on pressure. So to do that, all we do is use, again, the beautiful property of state functions is that we can choose any path as long as we start and end at the same places. So what we're going to do is we're going to choose a path that's reversible. We're going to assume ideal gas behavior just because the calculations are easier. And starting from the same point, okay, Gibbs energy at temperature, some pressure is equal to the Gibbs energy under standard states plus integral VdP. Now what we do is, ideal gas, V equals nRT over P. So nRT over P, we substituted for V. And now we can integrate the pressure. And so we get another useful equation, the Gibbs energy this is usually 298.15 Kelvin, and some pressure is equal to the Gibbs energy under standard states, standard conditions. Pressure is 1 bar, temperature 298.15, plus nRT ln of the final pressure over 1 bar. That's going to be 1 bar because it's standard states. This graph shows what happens to basically to Gibbs energy as the pressure changes. As pressure, because this axis here is the pressure over 1 bar, so the pressure without any units. This is the Gibbs energy, the molar Gibbs energy at some pressure, as the pressure changes, minus Gibbs energy at 1 bar, 298.15 Kelvin, standard molar Gibbs energy. And so what happens is, as the pressure goes to 0, the Gibbs energy asymptotically approaches negative infinity. We can kind of see this because we know that when pressure goes to 0, the volume of a gas is going to go to infinity. And from this equation up here, which we derived in Chapter 5, delta S is nR ln of V final minus V initial. That means that delta S is, S final minus S initial. So as the volume goes to infinity, delta S goes to infinity, which means that final, the entropy goes to infinity. And looking over here at the definition of Gibbs energy, H minus Ts, as S goes to infinity, because the volume is going to infinity, Gibbs energy goes to negative infinity. That's what's happening here. Okay, so now we're going to look at how Gibbs energy depends upon temperature. It ends up, real soon in this chapter, we're going to talk about equilibrium constants. And it's going to be useful to know how G over T, Gibbs energy over the temperature, depends upon the temperature. So what we do is we're going to take partial G over T with respect to T at constant P, and just going to apply the chain rule, because there's 2 parts to this. Is just we pull the 1 over T out front, 1 over T partial T constant P, plus pull the G out, G partial 1 over T partial T constant P. That's kind of cool because the second term here, there's just temperature in here, so we can make this an exact differential, d1 over T over dt. And now we can do that integral because d1 over d dt is going to be negative 1 over t squared. So we have g over t squared, negative g over t squared. And again, we showed earlier that partial g partial t constant p equals negative entropy. So we'll replace this term here with negative s, and we're getting to something pretty simple. So just a little bit of algebra here. We just multiply this term by t over t, 1. And we get t squared in the bottom, so we can combine terms. We get negative, the whole in front of the whole thing, ts plus g. But g is h minus ts, so the ts cancels, and we get negative h over t squared. Right? This is called the Gibbs-Helmholtz equation. And it says that the partial of g over t with respect to t at constant p is equal to negative h over t squared. We could also take the partial of g over t with respect to 1 over t at constant p. But this we can just write as partial g over t, partial t times dt over d1 over t. This would be partial t over partial 1 over t. This is just an equivalent way of writing this. But now because it's just temperature, we can write it as an exact differential. And we already showed that this term right here is equal to negative h over t squared. Dt with respect to 1 over t is just negative t squared. So the t squareds cancel, negatives cancel, and we just get enthalpy. Right? So this is another form of the Gibbs-Helmholtz equation. It says the partial of g over t with respect to 1 over t at constant p is equal to enthalpy. What we can do now, guys, is we can multiply through by partial 1 over t and make both sides. Now we can make both sides exact differentials. Integrate the left side from initial to the final temperature, same thing for the right. Make the g delta g and the h delta h. We can do that because delta g is just g final minus g initial, so the integral applies to both of them, so that's easy to do. Anyway, so now that we have this, okay, it's really easy to solve. Integral of d delta g over t is just delta g over t at t final minus delta g over t at t initial. So delta g at t final over t final minus delta g at t initial over t initial. Likewise here, okay, what we're going to do here, guys, is we're going to assume that enthalpy does not change appreciably over the temperature range of interest. It's probably a pretty good assumption. And so that means we can pull the delta H out front and use the delta H at the initial temperature, and we just get 1 over T final minus 1 over T initial. If it does change over the temperature range of interest, then it gets messier, but we can do that. Can do this. Okay, so this dependence of G on P, pressure and temperature, we can do the same thing for Helmholtz energy. Its dependence on volume and temperature. And it ends up that you do the same sort of analysis. You get partial A, partial T, constant V equals negative S. Partial A, partial V, constant T equals negative P. Likewise, A at the temperature final volume equals A at temperature initial volume minus integral from V initial to V final of PdV. And again, if we choose a reversible path, constant temperature and ideal gas, we get here that the Helmholtz energy under constant temperature at some volume is equal to the Helmholtz energy, same temperature at the initial volume minus nRT ln of V final over V initial. Again, ideal gas. You should go back and do these derivations. They follow directly the way that we did it for Gibbs energy. Likewise, just like we got the relationship between Gibbs energy over temperature on enthalpy, you can do the same thing for internal energy for Helmholtz energy. So it ends up doing the same sort of analysis. Partial A over T, partial T constant V equals negative internal energy over T squared, or partial A over T, partial 1 over T constant V equals just internal energy. And at constant volume, we get the same sort of equation as we did for Gibbs energy. Delta A at the final temperature over the final temperature is the approximate just assumes that the internal energy does not depend upon the temperature over the temperature range of interest. Delta A at initial temperature over the initial temperature equals delta U at that temperature times 1 over T final minus 1 over T initial. You guys should also derive this yourself. So real quickly, why do we care? What use is this? Well, a real simple example is you can look up in the back of your textbook and CRC handbook, like a lot of places, delta G of formation of different species, delta H of formation. So let's say silicon, okay, the delta G, it ends up the delta G of formation under standard states of silicon gas is this number, 405.5 kilojoules per mole. And its heat of formation is 450 kilojoules per mole, both at 298.15 Kelvin. We're going to assume that the delta H of formation doesn't change much over, 280 to 575 Kelvin, because we want to calculate delta G of formation of gaseous silicon at 525 Kelvin. So we just basically plug into this equation we derived, which is this one right here, where the final temperature will be 525 Kelvin, the initial will be 298.15. We plug in our delta G at 298.15, this right here, delta H, this right here. Multiply both sides through by the final temperature, which is 525, and plugging our numbers in. Oops, forgot a bracket. And we end up getting 372 kilojoules per mole. You should check my numbers as always, please. So that's that section.